Welcome back. Let's practice working with tangent vectors. All right, so here's our first example. We want to find the point of tangency and tangent vector at t equals 2/3 for this vector function. And our vector function is r of t is equal to a vector with components of 3t and 9t squared. So the first thing that's important to realize here is that we are working with a two-dimensional vector function. This vector function will represent a plane curve, not a space curve. We'll look at space curves in other examples in this video. But to start, we're going to keep things simple with a 2D vector function. And before we do anything here, before we try to find a point of tangency or the tangent vector at this specific value of t, since we're just working with a plane curve, I do want to try to draw a picture so that you can see what this tangent vector will look like once we find it. All right, this is not a requirement for these examples. You do not need to draw a graph of the curve represented by the vector function, but it certainly will help you understand what you're doing. All right, so to begin, let's determine what this curve will look like. From the components of the vector function, we know that x equals 3t and y equals 9t squared. So what we want to do is eliminate the parameter here, and then the resulting equation will help us sketch the curve. And so the easiest way to go about that is to solve for t in one of these two equations and then plug it into the other equation. And I think it will be easier to solve for t in this equation. We just have to divide both sides by 3. So in this case, t will be equal to x divided by 3, which then plugging that into this equation will give us y equals 9 times x divided by 3 squared. Now x squared will be x squared, and 3 squared is 9, so we have 9 divided by 9, so those two values will cancel out, just giving us y equals x squared. Okay, so a pretty simple equation. We are very familiar with the graph of y equals x squared. It's your very basic parabola. So I'll draw that here real quick. It will look something like this. That is our vector function, r of t. And do note that the vector function would be represented by this entire curve, not just a section of it or a part of it, because we have no restricted domain, and 3t and 9t squared are defined for all values of t. But now that we have a sketch of our plane curve, let's work on finding what we actually need to find in this example, which is the point of tangency and tangent vector at t equals 2/3. To find the point of tangency, that's just the point where we are finding a tangent vector at, and that point will be determined by this value of t. We simply just want to plug that value of t into our vector function. So for the point of tangency, we'll have r of 2/3, and that will be equal to 3 times 2/3, comma, 9 times 2/3 squared. Okay, now these two 3's will cancel out, so the x component is just 2. And then we have 2 squared, which is 4, divided by 3 squared, which is 9. And so those 9's will cancel out. So the vector that results here will be 2, 4. And so the point of tangency is the point 2, 4. All right, so that's our first answer to this problem. The point of tangency for t equals 2 divided by 3 is the point 2, 4. That is the terminal point from this vector that we got when we plugged in that value of t into the vector function. So let's actually plot that on the plane curve here. If this is x equals 1, x equals 2, and this is y equals 1, 2, 3, and 4, then our point 2, 4 would take us right here. That would be the point along this plane curve that we are working with. All right, that is where t equals 2/3. All right, so now we have the point of tangency. Now what we need to find is the tangent vector at that value of t. And to find a tangent vector, what we have to do is take the derivative of our vector function. Remember that the derivative of a vector function is a tangent vector for any value of the parameter t. All right, and then you can plug a specific value of t into that derivative to get the specific tangent vector. All right, so let's find the derivative here. R prime of t will be equal to 3, 18t, right? The derivative of 3t is 3, and the derivative of 9t squared is 18t because you multiply 2 down and subtract 1 from the exponent. Okay, so now let's evaluate that at our value of t. We'll have r prime of 2/3 is equal to 3, 18 times 2/3. Now, 18 times 2 is 36, and 36 divided by 3 is 12. So what we get here is 3 comma 12. And we could simplify that vector by pulling out a common factor of 3. So we could rewrite this to be 3 times 1 comma 4. Okay, so that would be the tangent vector at that specific value of t for this vector function. And so really that's it. That's all you have to do for this example. But I do want to show you what that looks like visually on our graph. Normally you would want to graph the tangent vector in this form, but I don't have a ton of space in my graph here to work with a y component of 12. So I'm just going to work with the shortened version of it. Remember that multiplying a vector by a scalar just changes its length. It doesn't change the direction or the way it's pointing or anything like that. So I'm just going to work with this vector right here for our tangent vector, a vector with an x component of 1 and a y component of 4. And the way we will plot this tangent vector is not by starting at the origin like we usually do, but rather starting at the point of tangency, because this is a tangent vector. It's tangent to this specific point on this curve. So from that point of tangency, we will move 1 in the x direction and 4 in the y direction. That will give us the terminal point of that vector, and we can see what the tangent vector would look like. So from our point of tangency, we'll move 1 in the x direction, and then 1, 2, 3, 4 in the y direction. So that would be the terminal point right there. And so then connecting those 2 points will give us a vector that looks like that. That would be r prime of 2/3. All right, and so you can see that this tangent vector is indeed a vector that is tangent to this point along this curve. And remember that to be tangent essentially means that you are taking the direction, or in this case, since we're working in 2 dimensions, the slope at that point and extending it to form a straight line, or in this case, a vector. All right, when we eventually look at space curves, you're no longer talking about slope, we're just talking about the direction within 3D space, but at least for a plane curve here, you can think of this tangent vector as having the slope of that point along this curve. And another thing to note here is that this tangent vector also tells us the orientation of our curve. Whatever direction the tangent vector is pointing in, that is going to be the direction or the orientation of the curve. So since this tangent vector is pointing in this direction, that means that this curve would be oriented in that direction. Okay, so that's something that you want to remember. A tangent vector gives you the orientation of the curve. It will always point in the direction that the curve is headed. All right, but that is it for this example. Let's take a look at another one. For this example, we want to find the point of tangency and tangent vector at t equals pi divided by 4. And we're working with this vector function, r of t is equal to 4 times cosine t times I plus 2 times sine t times j, where our values of t are restricted to be between 0 and 2 pi. Okay, so once again, we are working with a plane curve. This is a vector function with only 2 components, an x component and a y component. So we are working with a curve in 2 dimensions, which would be a plane curve. And so because we're working with a plane curve, I am once again going to draw a graph of our curve just to help us get a visual of what we're doing here. But once again, you don't have to draw the graph. It's not necessary to find the point of tangency and tangent vector. You can do it completely computationally, but I do want to show you what the point of tangency and tangent vector look like. All right, so to begin, let's draw a sketch of this plane curve. For our vector function, the x component is 4 times cosine t, and the y component is 2 times sine t. So we have x equals 4 times cosine t, comma, y equals 2 times sine t. All right, and so we have to eliminate the parameter here to get an equation that we can graph or sketch in the xy plane. And when you're working with sine and cosine, remember that you're probably going to want to make use of the Pythagorean identity, specifically the identity that cosine squared t plus sine squared t equals 1, right? That is the Pythagorean identity for sine and cosine. That's typically what you want to use to eliminate the parameter when working with 2 parametric equations that involve sine and cosine. All right, so what we should do here is just solve for cosine and sine in each of these equations and then plug what they're equal to into the identity. So we'll have x divided by 4 equals cosine t, and y divided by 2 equals sine t. So then plugging what sine and cosine are equal to into this identity will give us x divided by 4 squared plus y divided by 2 squared equals 1. All right, and then simplifying that will give us x squared divided by 16 plus y squared divided by 4 equals 1. And that right there is the equation of an ellipse, right? Whenever you have x squared and y squared divided by two different values, and those two terms are being added together and they equal 1, that is the equation of an ellipse. And to determine how to draw that ellipse, you can determine the distances along the x and y axes from the origin by looking at the denominator of the x and y terms. Just take the square root and you'll get the distance. So in the x direction, the square root of 16 is 4. So we'll be measuring 4 in the positive x direction and negative x direction. And then for y, the square root of 4 is 2. So we'll be measuring 2 in the positive y direction and negative y direction. And really, you can think of those as the intercepts. So from this equation of an ellipse, we know that x will be equal to plus or minus 4, and y will be equal to plus or minus 2. So if this is y equals 2, this is y equals negative 2, this is x equals 4, and this is x equals negative 4, our ellipse will look something like this. Okay, that would be our vector function r of t. And it is important to note here that although our domain is restricted from t equals 0 to t equals 2 pi, that would account for an entire loop of this ellipse. If you were to plug in t equals 0, you would get the point 40, which would take you right here, and you would get the same thing for 2 pi. So you would make a full ellipse for all the values of t in between 0 and 2 pi. Okay, so we don't have to make any adjustments to our graph here. We don't need to work with a specific part of the ellipse. This vector function on this interval represents the entire ellipse. Okay, but now that we have sketched our vector function, we now have a visual to go along with our work of finding the point of tangency and tangent vector, so we can make sense of what we're doing here. And so now let's actually work on finding those two things. To start, let's find the point of tangency. We just have to plug this value of t into our vector function. So for the point of tangency, we'll have r of pi divided by 4, which will be equal to 4 times cosine of pi divided by 4 times I plus 2 times sine of pi divided by 4 times j. Now cosine of pi divided by 4 is the square root of 2 divided by 2, and so is sine of pi divided by 4. They're equal to the same thing. So what we get here is 4 times the square root of 2 divided by 2 times I plus 2 times the square root of 2 divided by 2 times j. Now simplifying, these 2's will cancel out, and 4 divided by 2 is 2. So we get a vector of 2 square roots of 2 times I plus the square root of 2 times j. So that is the vector that we get when we plug in this value of t into our vector function. And so the point of tangency will be the terminal point of this vector, which would just be a point with an x-coordinate of 2 square roots of 2 and a y-coordinate of the square root of 2. All right, so our point of tangency is 2 square roots of 2, comma, the square root of 2. That is the first answer to this example. That is the point of tangency at that value of t. And so let's quickly plot that on our graph here. If you plug the square root of 2 into your calculator, it's approximately 1.4, and so 2 square roots of 2 would be 2.8. So going to our graph here, 2.8 in the x direction takes us about here. We're almost at 3, and then 1.4 in the y direction takes you about here. So that's our point of tangency. I'll plot that point right there. That's approximately where it would be. That is where t equals pi divided by 4. And so now we want to find the tangent vector at that value of t, or at that point on this plane curve. All right, and so to find the tangent vector, we have to take the derivative of our vector function. So let's do that. We'll have r prime of t is equal to the derivative of 4 cosine t. The derivative of cosine is negative sine, so we'll have negative 4 times sine t times I, and then plus the derivative of 2 sine t, and the derivative of sine is cosine, so we'll have 2 times cosine t times j. All right, now what we want to do is evaluate this derivative at t equals pi divided by 4, because this derivative represents the tangent vector for any value of t on this vector function, but if we evaluate it at t equals pi divided by 4, we get the specific tangent vector for that value of t. So we'll have r prime of pi divided by 4 is equal to negative 4 times sine of pi divided by 4 times I plus 2 times cosine of pi divided by 4 times j. All right, now once again, sine of pi divided by 4 and cosine of pi divided by 4 are both the square root of 2 divided by 2. So this will become negative 4 times the square root of 2 divided by 2, which will be negative 2 square roots of 2 times I, and then we'll have 2 times the square root of 2 divided by 2, which will give us the positive square root of 2 times j. All right, so that is our tangent vector at our value of t equals pi divided by 4. That would be the final answer to this example, but once again, I do want to show you what it looks like visually on our graph. So what we're going to do is sketch this vector by making its initial point our point of tangency. All right, so that's where we're going to start, and from that point, we are going to measure negative 2 square roots of 2 in the x direction, and the positive square root of 2 in the y direction. All right, so approximately that's negative 2.8, and then positive 1.4. So from this point of tangency, we will go negative 2 square roots of 2, or negative 2.8, so that takes us back to the y-axis, and then we want to move positive 1.4 in the y direction, so that would take us to about here. All right, so I'll plot that point right there, and then we'll connect our 2 points to create our tangent vector. It will look something like this. That would be r prime of pi divided by 4, and you can clearly see that this vector is tangent to that point along this ellipse. Whatever the slope would be at that point along this curve, this tangent vector takes that slope and extends it. Okay, and the tangent vector is pointing in this direction, so we know that the orientation of this ellipse would be in this direction. All right, the tangent vector always gives you the orientation of the curve represented by your vector function. All right, but with that, we have now found both the point of tangency and the tangent vector at t equals pi divided by 4 for this vector function, and so we are done with this example. For our next example, we're going to do something a little bit different. We want to find a set of parametric equations for the tangent line at t equals 2. And we're now working with a vector function in 3 dimensions. So this vector function represents a space curve because we have an x, y, and z component. And when we work with space curves or vector functions in 3 dimensions, we can do a lot more with tangent vectors. Specifically, we can find a set of parametric equations for a tangent line. All right, so we're still working with the same concepts, the same ideas that we worked with in the first 2 examples, but we're going to take it one step further. Because what we have to do to find a set of parametric equations for a tangent line is find both a point of tangency at the specific value of t and a tangent vector for that specific value of t. Because remember, to set up a set of parametric equations for a line in 3D space, you need both a point and a direction vector. And that's exactly what we're going to find here. The point of tangency at this value of t will be the point for the set of parametric equations, and the tangent vector at that value of t will be the direction vector for the tangent line that we need in order to set up the parametric equations. Okay, and so if you're not familiar with the parametric equations for a line in 3D space, feel free to go back to my lesson video on lines in 3D space. And one more thing, for these examples in 3 dimensions, I'm not going to draw a sketch by hand because it would just take too long and would deviate from the point of this video. And so after we find the parametric equations for the tangent line, I will simply just show you a 3D render of the curve and the tangent line on the screen. Okay, so you'll see what I'm talking about later on. But for now, let's just focus on the task at hand here. In order to find a set of parametric equations for the tangent line at t equals 2 for this vector function, we first need to find a point. And so that would be the point of tangency. So what we want to do is plug this value of t into our vector function. So the point of tangency, we can find that by taking r of 2, and that will give us 2 times I plus 4 times j plus 8 times k, right? T is 2, 2 squared is 4, and 2 cubed is 8. And so the vector that we have here has a terminal point of 2, 4, 8, and so that would be the point of tangency at t equals 2 for this vector function. Okay, so this is going to be the point that we're working with, 2, 4, 8. And so now we have our point for our tangent line. Now we need a direction vector, and that's going to be our tangent vector at this value of t. So to find that tangent vector, we have to take the derivative of our vector function. And so we'll have r prime of t is equal to I plus 2t times j plus 3t squared times k. Right? The derivative of t is 1, the derivative of t squared is 2t, and the derivative of t cubed is 3t squared. We just use the power rule for derivatives in each case. All right, and then we want to evaluate that derivative at 2 to get the specific tangent vector at that point. So we'll have r prime of 2 equals I plus 2 times 2, which is 4. So we'll just write 4j, and then plus 3 times t squared. So 2 squared is 4. 4 times 3 is 12. So we have 12k. All right, so that is the tangent vector at t equals 2 for this vector function. And so now that we have both a point and a direction vector, which also happens to be a tangent vector, we can create a set of parametric equations for the tangent line at this point on this vector function. Remember that the form of a set of parametric equations for a line in 3D space looks like this. The x equation will have the x component of the direction vector, which we call a, multiplied by t, plus the x coordinate of the point, so we call that x1. Then the y equation is y equals b times t, where b is the y component of the direction vector. And then you add y1, which is the y coordinate from the point. And then for z, you have z equals c times t plus z1, where c is the z component of the direction vector and z1 is the z coordinate from the point. So if we set up our parametric equations up here, this will be our final answer. We'll have x equals a, the x component of our direction vector, or the tangent vector in this case, which is 1. So we'll have 1 times t, which is t, plus the x coordinate of our point, which is 2. Then for y, the y component of the direction vector is 4. So we'll have 4t, and we'll add the y coordinate of the point of tangency, which is 4. So we have 4t plus 4. And then finally for z, that will be equal to our z component of the direction vector, which is 12, multiplied by t. So we have 12t, and then we'll add the z coordinate from our point, which is 8. So we have 12t plus 8. And that right there would be a set of parametric equations for the tangent line at t equals 2 for this vector function. Okay, and so to get an idea of what that looks like graphically, I'll put the 3D render up here on the screen now of the space curve represented by this vector function, along with the tangent line at t equals 2 represented by the parametric equations that we just set up. Okay, so in 3 dimensions, we don't really think of the tangent line as taking the slope at a point and extending it because we don't really have slope in 3 dimensions, but rather it's just taking the direction at that point along the curve and extending it. Okay, that's what a tangent line does in 3 dimensions. But with that, that is it for this example, and so let's take a look at another one. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful, then I'd invite you to join my membership site JK Math Plus, where you get access to many perks including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I will have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's take a look at the next example. Next up, we want to find a set of parametric equations for the tangent line at t equals pi divided by 6 for this vector function. We have r of t is equal to a vector function with components of 2 times sine t, 2 times cosine t, and 5. And so the first thing we want to do here to find a set of parametric equations for a tangent line is find both the point of tangency and the tangent vector for t equals pi divided by 6. Let's start with the point of tangency. We can find that by just plugging pi divided by 6 into our vector function. So for the point of tangency, we'll have r of pi divided by 6 is equal to 2 times sine of pi divided by 6. Then we'll have 2 times cosine of pi divided by 6, and then 5. And so then simplifying, sine of pi divided by 6 is 1/2. So this is equal to 2 times 1/2. And then cosine of pi divided by 6 is the square root of 3 divided by 2. So we have 2 times the square root of 3 divided by 2, and then 5. And so then these 2's will cancel out, and so will these 2's. 2 times 1/2 is just 1. So our vector here is 1, the square root of 3, 5. And so that vector gives us a point of tangency of 1, the square root of 3, 5, right? This is the vector that results from our vector function when we plug in pi divided by 6, but the terminal point of that vector would be the point of tangency, which has coordinates of 1, the square root of 3, and 5. All right, so that's going to be the point that we use to create a set of parametric equations for the tangent line. But now we also need a direction vector, or more specifically, the tangent vector for this vector function at t equals pi divided by 6. So now what we want to do is take the derivative of our vector function and evaluate it at pi divided by 6. So let's do that. We'll have r prime of t is equal to 2 times cosine t, and then negative 2 times sine t, and 0, right? The derivative of sine is cosine, so we have 2 cosine t. The derivative of cosine is negative sine, so we have negative 2 times sine t. And the derivative of a constant, such as 5, is 0. All right, so this is our tangent vector for any value of t, but we want to evaluate it at t equals pi divided by 6 to get a specific tangent vector. So we'll evaluate r prime of t at pi divided by 6, and that will give us 2 times cosine of pi divided by 6, and then negative 2 times sine of pi divided by 6, and then the z component stays the same. It's just 0. All right, now if we simplify, once again, cosine of pi divided by 6 is the square root of 3 divided by 2, so this will become 2 times the square root of 3 divided by 2, and then we have negative 2 times sine of pi divided by 6. Sine of pi divided by 6 is 1/2, so we have negative 2 times 1/2, and then 0. And then simplifying, these 2's cancel out, and so do these 2's. So what we're left with is a vector with components of the square root of 3, negative 1, and 0. So that's our tangent vector for t equals pi divided by 6 on this vector function. Now what we want to do is put everything together. We want to use our point of tangency and our tangent vector to create a set of parametric equations for the tangent line. And so once again, remember the form of a set of parametric equations for a line in 3D space. You'll have x equals a times t plus x1, y equals b times t plus y1, and z equals c times t plus z1. All right, a, b, and c are the x, y, and z components of the direction vector, or in this case, the tangent vector, and x1, y1, z1 are the coordinates of our point of tangency. So here's what we're going to have. We'll have x equals the square root of 3 times t plus 1, y equals negative t plus the square root of 3, and z equals 0 times t, so just 0 plus 5, so z equals 5. All right, so the square root of 3 was the x component of the tangent vector, 1 was the x coordinate from the point of tangency, negative 1 was the y component of the tangent vector, and the square root of 3 was the y coordinate. And then as we just went through, 0 is the z component of the tangent vector, so 0 times t is 0, and then z1 is 5. Okay, so that right there is a set of parametric equations that represents the tangent line at t equals pi divided by 6 for this vector function. And just like I did with the previous example, instead of trying to draw a sketch by hand, I'll just show you a 3D render here of what the space curve for this vector function looks like, as well as the tangent line that does touch the point where t equals pi divided by 6. Okay, we could certainly sketch the space curve ourselves by hand, but in the interest of time and just focusing on the new concepts in this video, I'm just going to provide you with this render. Let's take a look at another example. Here we once again want to find a set of parametric equations for the tangent line at t equals 3, and for this vector function. We have r of t is equal to e to the power of 3 minus t times I plus sine of pi t divided by 3 times j plus the square root of 3t times k. Okay, so once again, we need to find two things. We need to find the point of tangency and the tangent vector for this value of t on this vector function. And so let's start with the point of tangency. To find the point of tangency, we want to evaluate r of t at 3. So we'll plug in 3, and we'll have e to the power of 3 minus 3 times I plus sine of pi times 3 divided by 3 multiplied by j, and then we have plus the square root of 3 times 3 times k. And so if we simplify, e to the power of 3 minus 3 will be e to the power of 0, so that's just 1. So we'll have 1 times I, and then these 3's will cancel out inside the sine function. So we have sine of just pi, and sine of pi is 0. So the middle term will be 0j. And then for the k term, we have the square root of 3 times 3. 3 times 3 is 9, and the square root of 9 is 3. So we have 3k. All right, and so from this vector that we get from plugging 3 into the vector function, we now know that the point of tangency will have the coordinates of 1, 0, 3. Okay, so that is our point of tangency. We will use that point to help us create a set of parametric equations for the tangent line, but before we can do that, we also need to find a tangent vector for t equals 3. So let's start by taking the derivative of our vector function. We'll have r prime of t is equal to the derivative of e to the power of 3 minus t. Remember that the derivative of an exponential function with a base of e is just itself multiplied by the derivative of the exponent. So we'll have e to the power of 3 minus t times the derivative of 3 minus t, which will just be negative 1. So we're multiplying by negative 1, and then we multiply by I. Then we need to take the derivative of sine of pi t divided by 3. That will require the use of the chain rule. We'll take the derivative of the outside function first, keeping the same inside function. So we have plus cosine of pi t divided by 3. And then you want to multiply by the derivative of that inside function, which is pi t divided by 3. Its derivative will just be pi divided by 3. So we're multiplying by pi divided by 3. And then don't forget that that is multiplied by j. And then finally, let's add the derivative of the k term. We have the square root of 3t. That could be rewritten to be 3t to the power of 1/2. And so we can take a derivative of that using the power rule for derivatives, but do notice that there is an inside function. It's not just t to the 1/2 power, it's 3t, so we will need to use the chain rule here as well. So we'll have 1/2 times 3t to the power of negative 1/2 multiplied by the derivative of 3t, that inside function, which is 3. Okay, and then we multiply by k. And so now we could try to simplify this, but we're just going to end up plugging 3 into it in order to find the specific tangent vector at t equals 3. So I'm not going to bother to simplify this. I'm just going to plug in 3, and then we'll worry about simplifying. So we'll take r prime of 3, and that will give us e to the power of 3 minus 3, and that's multiplied by negative 1, so this is a negative term, and then that's multiplied by I, and then we have plus cosine of pi times 3 divided by 3 times pi divided by 3 times j, plus 1/2 times 3 times 3 to the power of negative 1/2 times 3 times k. All right, so now e to the power of 3 minus 3, that's just e to the power of 0, which is 1, but don't forget about that negative. So this is equal to negative I, and then these 3's will cancel out. So we have cosine of pi, and cosine of pi is negative 1. And so we have negative 1 times pi divided by 3. So we'll have minus pi divided by 3 times j, And then for the last term, things get a little bit tricky, but it's nothing we can't handle. Remember that a negative 1/2 power is the same as a square root, but in the denominator. So really, the way that we could write this here would be 1 divided by the square root of 3 times 3, all right? And so 3 times 3 is 9. The square root of 9 is 3. And so we have 3 in the denominator and 3 over here. So those are just going to cancel each other out. And so we're just left with 1/2 times k. All right. So we have plus 1/2 k. And that is our tangent vector, specifically the tangent vector at t equals 3 for this vector function. And so now that we have both our point of tangency and the tangent vector, we can use those two things to create a set of parametric equations that represent the tangent line at that value of t on the vector function. So let's do that. I'll start with the x equation. We're going to take the x component of our tangent vector, which is -1, multiply it by t, so we have negative t, and then we want to add the x coordinate of the point of tangency. So we have negative t plus 1. Then let's move on to the y equation. That will be equal to the y component multiplied by t. So we have negative pi divided by 3. So we have negative pi divided by 3 times t, and then adding the y coordinate of our point. Well, it's just 0, so there's nothing to add. We'll just leave that equation as it is. And then finally, we have the z equation. We'll take the z component of the tangent vector, which is 1/2, and multiply that by t, and then add the z coordinate from the point of tangency, which is 3. So we have plus 3. And that right there is a set of parametric equations that represents the tangent line at t equals 3 for this vector function. And if you want to see what that looks like with a graph, I'll put a 3D render up here on the screen for you to look at. You can see the curve represented by this vector function, as well as the tangent line at t equals 3 along that curve. Okay, and so that's it for this example. And this is going to be our last example of finding a set of parametric equations for a tangent line. What I want to do for our last few examples is find some unit tangent vectors. And so first up, we want to find the unit tangent vector at t equals pi divided by 2 for this vector function. It is a vector function with just two components, an x component of 6 cosine t and a y component of 2 sine t. Now, finding a unit tangent vector is not all that different from finding a regular tangent vector. We're still going to take the derivative of our vector function to find a tangent vector, but then once we have that, what we're going to do is then divide it by its magnitude, right? The only difference between a regular vector and a unit vector is that a unit vector has a length of 1. And so to get that length of 1, you have to divide the vector by its own magnitude. And that's exactly what we're going to do here. The only thing you want to remember is that a unit tangent vector has its own special notation that looks like this. It's a vector function, capital T of t. And as I've already explained, we can find a unit tangent vector by finding the derivative of a vector function and dividing it by its magnitude, because the derivative of a vector function is a tangent vector. Okay, so if you divide that tangent vector by its magnitude, then you get a unit tangent vector. It will be a tangent vector with a length of 1. All right, so let's work on finding these two pieces that we need, and then once we have that set up, we can just plug pi divided by 2 into the unit tangent vector, and we'll have our answer to this problem. All right, so let's start with the derivative, r prime of t. We'll take the derivative of the x component. The derivative of cosine is negative sine, so we have negative 6 times sine t, and then the derivative of sine is cosine, so we have 2 times cosine t. Okay, and then the magnitude of that vector, let's find that. We're going to take the magnitude of r prime of t, and remember, to find the magnitude of a vector, you take the square root of the sum of the components squared. So we'll have negative 6 times sine t squared plus 2 times cosine t squared. All right, so now let's put these two things together and create a unit tangent vector. Capital T of t will be equal to negative 6 times sine t, comma 2 cosine t, divided by its magnitude, which now will simplify. We have 36 sine squared t plus 4 cosine squared t. And so now let's plug in pi divided by 2 and see what our unit tangent vector will be. We'll have capital T of pi divided by 2, and that will be equal to -6 times sine of pi divided by 2, and then 2 times cosine of pi divided by 2, divided by the square root of 36 times sine squared of pi divided by 2 plus 4 cosine squared of pi divided by 2. Okay, so then to simplify, sine of pi divided by 2 is 1, and cosine of pi divided by 2 is 0. So here's what we'll get. We will have the vector -6, 0, and then instead of dividing it by the magnitude, I'm just going to move the magnitude out front. So we'll have 1 divided by the magnitude multiplied by the vector. So we'll have 1 divided by the square root of 36 times sine squared of pi divided by 2. As we said, sine of pi divided by 2 is 1. 1 squared is 1. So we have 1 times 36. So we have the square root of 36 plus 4 times cosine squared of pi divided by 2. Cosine of pi divided by 2 is 0, so 0 squared is still 0. 0 times 4 is 0, so we're just adding 0. So we have 36 plus 0 inside the square root. And so really, we just have the square root of 36, which is 6. So the final answer here would be 1/6 times -6, 0. And if you wanted to, typically it's not helpful to do this because usually that magnitude is so ugly. But in this case, since it's not ugly, you can multiply that through here and get an even nicer vector. -6 times 1/6 would just be -1. So while I usually don't recommend that you distribute 1 divided by the magnitude through the vector, either answer would be fine here. This is how I would usually write it. But if you want to, you could also write that this is equal to a vector with components of -1 and 0. Okay, so that's also fine. Ultimately, it's up to you, but both answers would be correct. It's just that one is a little bit more simplified. Okay, but with that, let's look at another example. Next up, we want to find the unit tangent vector at t equals 1 for this vector function. This time we have a vector function with 3 components. The x component is t, the y component is t squared, and the z component is the natural log of t. All right, so let's find the unit tangent vector for t equals 1. Let's start by finding the derivative of our vector function. If we take the derivative of each component individually, we'll get 1, 2t, and 1 divided by t, right? The derivative of t is 1, the derivative of t squared is 2t, and the derivative of the natural log of t is 1 divided by t. And then let's find the magnitude of that vector function, because not only is this the derivative of this vector function, it also represents the tangent vector for this vector function. So we want to find the magnitude of the tangent vector so that we can divide the tangent vector by its magnitude to get a unit tangent vector. All right, so the magnitude of r prime of t will be equal to the square root of the sum of the components squared. So we have 1 squared plus 2t squared plus 1 divided by t squared. All right, and so now let's set up our unit tangent vector. We'll have t of t, or capital T of t, is equal to the tangent vector 1, 2t, 1 divided by t, divided by its magnitude. And I'll simplify it a little bit. 1 squared is 1, 2t squared is 4t squared, and 1 divided by t squared will be 1 divided by t squared. All right, so we'll have the square root of 1 plus 4t squared plus 1 divided by t squared. And so now let's evaluate this at t equals 1. We'll have capital T of 1 is equal to a vector with components of 1, 2 times 1, and 1 divided by 1. And we're dividing by the square root of 1 plus 4 times 1 squared plus 1 divided by 1 squared. All right, and so then simplifying, we have 1, 2, and 1 as our vector components, and then we're dividing by the square root of 1 plus 4 plus another 1 is 6, right? 1 divided by 1 squared is 1, so we have 1 plus 4 plus 1, which is 6. So our final answer here, if we pull out that magnitude being divided into 1, we have 1 divided by the square root of 6 times a vector with components of 1, 2, 1. All right, that would be the unit tangent vector at t equals 1 for this vector function. And in this case, since that magnitude was not as nice, it's a square root. I'm just going to keep this scalar value on the outside of the vector. That's just a good habit to get into because when we go to use these unit tangent vectors in the future in Calculus 3, working with them in this way will be a lot nicer than if you were to make all of the vector components more complicated by multiplying 1 divided by the square root of 6 into each of them, okay? It's going to be easier to keep that outside of the vector so you have nicer components. Okay, but that's it for this example. Let's take a look at one more for this video. For our last example, we want to find the unit tangent vector at t equals 0 for this vector function. R of t is equal to e to the power of t times sine t times I plus e to the power of t times cosine t times j plus e to the power of t times k. All right, so once again, the process remains the same. To find a unit tangent vector, we want to start by finding the tangent vector by taking the derivative of our vector function and then finding the magnitude of that tangent vector and dividing the tangent vector by that magnitude. All right, so let's start by finding the derivative of our vector function. We'll have r prime of t is equal to the derivative of this component, which features a product of two functions, so we will have to use the product rule here. We'll have e to the power of t, which is the first function, times the derivative of the second. The derivative of sine is cosine. And then we'll add that to the second function times the derivative of the first, but the derivative of e to the power of t is just itself, so we're multiplying by e to the power of t. That is all multiplied by I. Then for the y component, we also have a product of two functions, so we have to use the product rule again. We'll have e to the power of t times the derivative of cosine, which is a negative sine, plus the second function cosine of t times the derivative of the first, and the derivative of e to the power of t, once again, is just itself, and that's all multiplied by j. And then for the last component, things get a little bit easier. We just have e to the power of t, and that derivative will just be itself, so we have e to the power of t times k. All right, now in the interest of keeping things as simple as possible, I think we want to try to simplify this before we take the magnitude of this vector. And what I notice is that in the x and y components, both of the terms in those components have a common factor of e to the power of t. So what I'm going to do is just simply pull that out to make those components a little bit nicer to work with. So if I do that here, we'll have e to the power of t times cosine t plus sine t times I. And then I'm going to do the same thing for this component, but I'm also going to reverse the order of addition here. Instead of having negative sine t plus cosine t, I'm just going to put the positive term first. So we'll have cosine t minus sine t. But both of them are still being multiplied by e to the power of t. So we have plus e to the power of t times cosine t minus sine t times j. All right, and then we still have plus e to the power of t times k. Now you might notice that all three of these components have a common factor of e to the power of t. We could pull that out, but I'm just going to leave it like that because I'm actually going to go about this calculation a little bit different than I did in the previous two examples. In the last two examples, I found everything in terms of t first and then plugged in the value of t that we're working with. But in this case, because of how messy this tangent vector is, I'm just going to plug in 0 to start with. So we'll have r prime of 0, which will be our tangent vector evaluated at t equals 0. And then I'll just find the magnitude of that and divide the tangent vector at t equals 0 by that magnitude, okay? You'll see what I mean. Let's work on evaluating r prime of t at 0. We'll have r prime of 0 is equal to e to the power of 0 times cosine of 0 plus sine of 0 times I plus e to the power of 0 times cosine of 0 minus sine of 0 times j plus e to the power of 0 times k. All right, now all of those e to the power of zeros, those are just going to become 1 because anything to the power of 0 is 1. And so really we just have to pay attention to cosine and sine here. Cosine of 0 is 1 and sine of 0 is 0. So what we get here is 1 times 1 plus 0 times I plus 1 times 1 minus 0 times j plus 1 times k. All right, all three of these components are just 1. 1 plus 1 is 1, times 1 is 1, so we have 1 times I, and then 1 minus 0 is 1, times 1 is 1, times j is just j, and then we already have 1 times k. So our resulting vector here is just I plus j plus k. That is our tangent vector for this vector function at t equals 0. So now you might see why you would like to do it this way rather than do it the way that I did in the previous 2 examples. Rather than working in terms of t and then plugging in the value of t, maybe you just want to plug in that value of t into the derivative right away, and then finding the magnitude of that tangent vector is a whole lot easier. So in this case, we just want to take the square root of the sum of the components squared, and all of our components are just 1, so that's going to turn out to be pretty nice. We will have that the unit tangent vector at t equals 0 is equal to our vector of I plus j plus k divided by its magnitude, or really I'm just going to multiply it by 1 divided by its magnitude. So we'll have 1 divided by the square root of 1 plus 1 plus 1, right? 1 squared is 1, so we just have 1 plus 1 plus 1, which is 3. Okay, so the magnitude of a vector where all 3 components are 1 is a square root of 3. So we have 1 divided by the square root of 3 times I plus j plus k. All right, that is the unit tangent vector at t equals 0 for this vector function. A little bit of an easier way to go about it than I have shown previously, but it can be helpful to know what your unit tangent vector is in terms of t before plugging in a value of t, so that's why I was showing it that way. But if you want to just get right to the chase and get right to that unit tangent vector for the specific value of t you're given, feel free to just plug that right into your tangent vector and then find its magnitude and divide it by that magnitude. Okay, and so with that, this was the last example for this video. However, I do have more available on my membership site, so if that's something that interests you, feel free to look into becoming a member. You can find all the details on my website at jkmathematics.com/plus. If you have any questions, please let me know in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.